Hi everyone, welcome to this webinar. So today we are very happy to have Benjamin Zhang from UMass Amherst, who is a postdoctoral research associate in the Department of Mathematics and Statistics with Marcos Katsoulakis, and after doing his PhD at MIT. So thanks a lot for accepting the invitation, and we are very much looking forward to your talk. So today, Benjamin is going to talk about the MFG Games Laboratory for Generative Modeling. So thank you, and the floor is yours.
Okay. Great. Thanks, Matthew, for inviting us to give this talk. So today, so I understand the audience, I assume, is mostly from like a mean-field games audience. So we'll be talking about a mean-field games or laboratory for generative modeling. So because I assume most people are mostly in mean-field games, so I'll do a quick recap of what is generative modeling first. So generative modeling is, it's very generative modeling, generative AI, depending on, I get different reactions depending on what words I use. If I say modeling, people don't react. If I say AI, everyone's like, oh, what's that, right? Very relevant, a very sort of hot topic these days, right? So from the more frivolous applications, like creating fake images with Stable Diffusion, or kind of talking to a machine with ChatGPT, to more sort of actual, more fruitful, impactful applications such as drug discovery. So this idea of how do you find possible good candidate molecules that may be helpful in drug for treating illnesses, or sort of creating more images of sort of private patient data. So, like for example, this is these data sets are data sets of cancer, and the idea is that because patient data is very private, at least in the US and Europe, it's very private. So there's not enough data to kind of train doctors on these images of cancer. So there's a lot of interest in sort of creating more images of fake cancer or fake images of real cancer, depending on how you see it, using generative modeling in this case. Okay, so from a mathematical standpoint, like how does this exactly work? So it's just think of it like this. So given some sort of data set of images, so in this case, for example, there's something called the Elson data set, which is a data set of images of bedrooms. And the idea is you're going to assume that this data set of images of bedrooms sort of is described by some sort of probability distribution. And so the idea of a generative model for this data set is to find some sort of a surrogate probability distribution, we'll call p theta, such that it kind of approximates the distribution, the real distribution that this bedroom lives on, in a way such that it's easy to sample from the surrogate distribution. So the idea is to, let's just say you have some family of distributions, you parameterize it with some parameters, and after you find some sort of probability distribution that approximates the distribution of images of bedrooms, then if you can sample from it, you can then generate new unseen images of possible images of bedrooms. Okay, so if you're familiar with sampling, it's very related to sampling. So you can kind of think of it as sampling is a situation where, given the distribution, you want to create samples, or to kind of sample from the probability distribution because you want to do Monte Carlo, or you want to explore some sort of energy landscape. And so the idea is like, okay, you know a distribution up to some sort of normalizing constant, and you figure out a way, an algorithm to produce samples from this. Whereas sort of generative modeling is a situation where you don't know what the distribution is. You only have samples, real samples from the distribution. And the idea is to kind of construct some sort of a surrogate distribution that kind of looks like the true distribution, and then you can just create new ones. So in this case, this really 1D example, this is the true distribution maybe in red, and you're only given samples in blue here. And if you want to create more of these samples, then the idea is to find some sort of a surrogate distribution, which is in green, and then produce more samples. So that's sort of the recap of what is generative modeling. So the idea is, given samples of a distribution, we want more of them. Okay. And if you're familiar with the generative modeling literature, or maybe you've heard these words over the last few years, there are very many
happening. Okay, sorry, please continue. It's okay.
Yeah, so there are many different approaches. You may have heard these words over the last few years. Many different approaches for generative modeling, things like GANs, generative adversarial nets, or normalizing flows, and et cetera. And score-based models or diffusion models is a very popular model these days. But then the ones we'll be focusing on today are these flow-based generative models, so based on sort of ODEs and sort of stochastic differential equations. So the first example is sort of this continuous normalizing flow, where the idea is maybe you have some sort of complex distribution, samples from a complex distribution up top here. And the idea is to find some sort of a way to learn an ODE that evolves a normal distribution. So that's a distribution that's very easy to sample from to your complex target distribution. Okay. The other class is the score-based random model. So the idea here is maybe you have this bimodal distribution you would like to create you have samples of and you would like to create more of. The idea is to add noise to samples of the distribution until it's basically all Gaussian. It's just pure noise. But as you add noise to the distribution, you learn how to denoise. So as you add noise, you also learn the process of learning how to denoise, because if you know how to denoise the distribution the right way, you can take new samples of the normal and then sort of apply the denoising process and get sort of new samples from your target distribution. And the third class, which is maybe some of you have heard of, this Wasserstein gradient flows. So this is actually a way to, in some sense, sometimes it's more of a theoretical tool to study generative models, and sampling methods. But there's been some recent work on sort of making implicit generative models. So the idea is maybe you have a cloud of samples and you don't really necessarily want a map, you just want an approximate distribution. You just want to figure out what the flow is, so that if you have a cloud of samples, how do you make this cloud of samples, in this case in pink, flow towards the sort of the distribution in blue here. Okay. And so today the idea is to, okay, on the other hand, there's the mean field game. So I won't go through too much of this. The idea is, okay, so we have, it's a way of modeling sort of dynamics of large populations of agents that sort of interact with each other. So in this case, in the case of modeling, how do schools of fish move? Each individual fish is moving around, but it's moving around according to the fish around it, and they make decisions accordingly. And then at the same time, based on the individual decisions of each fish, the mass for the school of fish evolve according to together as a whole as well, in a sort of a mean field way. Okay. So the motivation of the talk today is, the purpose of the talk today is to just kind of view mean field games as a sort of a unifying mathematical framework for generative modeling, and we'll explore sort of three ways in which this will happen. So the first is sort of understanding mean field games as a way for explaining generative modeling. So part of the motivation of the paper was sort of at least when I first got into generative modeling, I felt there was overwhelmed by the number of papers out there, right? Everyone has their own method. Some people use flow, some people use diffusions, and some people use one divergence versus another, and it's very sort of like, it's really hard to kind of sift through all this mass of literature. So one thing that this mean field games sort of a framework does is sort of organize all of these different papers, so you can understand how these generative models are related to each other in effect. Okay. But of course, like mean field games on its own is a very sort of well-developed mathematical field. So based on sort of knowledge about mean field games, it can inform sort of mathematical structure inside of generative models. So if you ever kind of try to create your own generative model, like in practice, there's a lot of neural nets running around, and neural nets are very unstructured mathematical objects, right? Or they can, because they're very flexible in terms of like approximating functions of interest, but at the same time, their structures somewhat opaque. They're very kind of amorphous, right? So, but the mean field games will sort of inform sort of like what the neural net should look like in effect. So we'll kind of explore that a little bit as well. But once we kind of put everything in sort of a unifying mathematical framework, then it's a very natural way to sort of just look at this framework and just start playing around with things. So we can start sort of inventing new generative models. So this then creates sort of a laboratory for experimenting with new models. Okay. So we'll go into a bit more specifics. So just to ground everyone in mean field games, I'm sure everyone in the audience may be a better expert at these things. Anyways, we're just going to say we have a lot of agents. Each agent evolves according to some sort of, and in this case, just an SDE. There may be noise, or maybe not going to be noise. And as the number of agents grows to very large, you describe them by some sort of a density. And the evolution of the density is described by some sort of Fokker-Planck or continuity equation, given some initial density of agents. Okay. To minimize its own personal cost function. And this cost function is dependent on things like running costs. So every time it makes an action or it does something, it incurs a cost. The costs of interacting with the other particles as it's moving, or other sort of agents as it's moving around, and sort of a terminal cost where it ends up relative to sort of other agents in the mass. Okay. And so what makes this sort of a game is that it's not, if you know, you might, at least the people who aren't familiar with mean field games, you might say, why isn't this just a control problem? Oh, well, yes and no. Yes, and it looks like a control problem, but in fact, each agent is dependent on sort of what all the other agents are doing according to the sort of density that's living inside this interaction and terminal costs. And this is what sort of makes it a game, in effect, where you have a lot of agents sort of competing against to minimize their own personal cost functions. Okay, and in particular, the formulation of mean field games we'll be using is the so-called potential mean field games. So this is basically just replace this sort of control-like optimization function problem into with a infinite dimensional optimization problem. Okay, so you still have a running cost, an interaction cost, and terminal cost in trying to find sort of the velocity field and the sort of the path on distribution on the space of distributions that will minimize this functional. Okay, subject to the fact that the densities have to evolve according to the Fokker-Planck or the continuity equation with some initial conditions. And one way to sort of study this optimization problem is just to go ahead and look at the optimality conditions. And how it goes is sort of, well, you first define a Hamiltonian based on the running costs. And then once you have the Hamiltonian, it will sort of describe what you can relate, you can sort of express the optimum velocity field in terms of the Hamiltonian and this function u, where the function u solves the Hammond-Jacobi equation, which is one of the two equations in the optimality condition. So this becomes, so I guess some people in mean field games would just consider the PDE, this system, as the mean field game, a coupled set of two PDEs, nonlinear PDEs, one Fokker-Planck, where the velocity field is related to the solution of the Hammond-Jacobi equation, and the Hammond-Jacobi equation is coupled to the Fokker-Planck in a way where you have a source term and these terminal conditions that are dependent on the solution of the Fokker-Planck. And this is the main reason why it's not necessarily just an optimization, not just an optimal control problem, but in fact a mean field game problem is because of this coupling between these two equations. Okay. And so, yes, so just to kind of make these in color, just to kind of keep track of all the terms, this running cost is sort of related to the Hamiltonian. The interaction cost appears as sort of a source term in the Hammond-Jacobi equation, and terminal costs corresponds to basically a terminal condition in the Hammond-Jacobi equation. Okay. So that's sort of the setup. That's the sort of the playground we'll play in, at least in mean field games. So based on these tools, we'll sort of study, next we'll study the different types of generative models within this framework. So you might wonder why mean field games for generative modeling. And we were kind of staring at different types of functionals that are used to train the generative models. And they all sort of just look like this. This is a very qualitative, hand-wavy description, okay? So the idea is that if a lot of these flow-based generative models, they kind of look like they're kind of solving some sort of a mean field game. Oftentimes there's some sort of a loss function that's some sort of a that describes the discrepancy between your true distribution and your approximate distribution. So true being pi and rho being your approximate distribution. And the generative model is some sort of ODE that sort of takes it from some sort of reference distribution and tries to push it towards some a distribution that approximates pi. And this loss function could be, if you sort of these like information divergences like KL divergence or cross entropy or F divergences. There are different, many different various choices that you can make. And sometimes they might add some sort of a transport cost. So, okay, most of the time they might just say L is 0. So in this case, they just look at this loss alone, but oftentimes they also say like, okay, well, if you want to include some optimal transport cost, you might put like a 1/2 V squared in here, for example. So already sort of like, oh, this sort of feels like a mean field game already, right? So what we'll kind of see is basically like not just like, it's not just that some general models are mean field games. We'll find that like basically all good ones are mean field games in the end. So the idea is that this is the sort of the status quo picture of generative modeling, right? Just this relationship. You have an optimization problem, and then you solve the optimization problem, you get some sort of a generative model, okay? But we'll take a sort of a bigger picture with the mean field games. And the idea is that this doesn't come from nowhere. It actually indeed comes
happening, but I guess you could, yeah,
Sure.
sorry, please continue. Sorry about that.
Okay. Yeah. So from the main field game, then okay. So at first you might wonder, okay, sure, why or what is the purpose? Or like, okay, sure, this is fine as a tool. But what this gives you, what does it give you, right? So what this gives you is sort of optimality conditions. So it sort of describes, gives a bit more mathematical structure behind what is generative modeling, right? So in this case, if you understand generative modeling as a mean field game, and we understand mean field games as basically this coupled set of PDEs, then it gives you sort of things like optimality conditions, well-posedness, and then gives you structure in the sense of like you can describe the optimal velocity field inside of a generative model in terms of the solution of the mean field game, and that which can then inform what the structure of the generative model should look like. And this is sort of then it becomes sort of a neat way of sort of looking at generative models. So there's like sort of a common backward-forward structure, backward being from the Hammond-Jacobi equation, forward from the Fokker-Planck, where the backward equation determines sort of the optimal velocity field in the forward of the generative model, and the forward equation just generates. And this happens to apply to all flow and diffusion-based models in the end. Okay. So we'll just kind of run through the various examples just to kind of demonstrate that this is indeed the case. Right? So the first case we'll look at is the normalizing flow. So just
Terry, can I ask a quick question on the
yeah.
previous slide? So on the previous slide, when you say generative modeling in the top right corner, you mean really generative models based on some dynamical formulation, right? I imagine you could have generative models that are maybe not based on SDEs or that, right? So here, but you are saying that for this class, then because the terminal constraint involve basically the target distribution or something like this, then it is, you can interpret it as a mean field game, and then you can use the optimality condition to find the optimal velocity field, basically, or the optimal control.
Right. Because it gives you, maybe, I mean, so of course these equations are hard to solve generally, but
yeah,
it may still give you sort of qualitative sort of structure inside of like what this velocity field should look like in your generative model.
I see. So something like, even if, because in practice, I guess you don't know the terminal distribution rho v at time t, because you don't know the data distribution. But
right.
what you're saying is somehow if you know the cost functions that you are using, then you can still get something about the formula that would give you v star or nu star. So you kind of know maybe the structures that nu star should have, maybe, or it can inform. Yeah, I see. Okay.
Right, exactly. So the next examples will sort of demonstrate that. It will show you without kind of truly learning doing any learning, you can already sort of know what the structure of the velocity field should look like in effect.
Okay, thanks. I think there is another question, maybe Romuald, if you want to.
Yes, thanks. Hi, quick question. So if I understand correctly, we will be mainly focusing on potential mean field games. And so I'm just curious about this connection between, let's say, the structural connection. I'm just wondering if you think it must be related to mean field games, or mean field control would make some sense here, in particular because it's potential. So there should be connection between the potential min-field games and the min-field control. And sometimes I don't really see why there must be a game. I understand this forward-backward structure, which is part of it, but I'm not sure I understand the game part.
Right. So like in the sense of why doesn't the thing just decouple in some sense, right? In a way where you just have a lot of like a mean field version of a control problem, you're saying.
Right? Yes, just out of curiosity. We can discuss this later. But it makes sense.
So we'll see the next step. So even for something like a normalizing flow, I think, yeah, so we've definitely gotten some feedback about like, oh, is a normalizing flow just control? We can actually see it's not just control, it's actually truly a game because the two equations, the Fokker-Planck and the Hammond-Jacobi, are truly coupled together, even without an interaction term, because of the terminal condition. But we can run through the next two examples real quick, and you'll kind of see why that is the case. Okay, so just to recap of normalizing flows, the idea. So this is the idea is to find some sort of a map, that takes some sort of a normal distribution to your sort of target distribution, and the idea to do that is to sort of minimize this KL divergence between your true distribution pi and sort of your approximate distribution f push forward of the normal distribution. And the usual way to do this is basically some sort of maximum likelihood estimator in this case, okay? But in the continuous, you can also do this in the continuous sense with an ODE. So in this case, right now, again, so it's instead of finding a map, you're trying to find a flow that will flow your normal distribution to your target. And this is the sort of the very standard set of normalizing flows. If you still write out min dKL, KL divergence between pi and f push forward rho, and you can actually compute this term, or this likelihood, or sorry, the log likelihood, by integrating a certain term along basically the divergence of the velocity field along the path in effect. Okay. And at least in practice, it's well noted that these continuous normalizing flows are ill-posed. So what I mean by that is, depending on how you parameterize the system, you may get different solutions in effect, right? You may get multiple solutions. And it's not that there's no solution, but oftentimes there may be multiple solutions involved, and so there's a lot of tuning involved. So that's already sort of well known. So what we're going to do is sort of study this continuous normalizing flows with the mean field game tools in effect. Okay, so CNFs are ill-posed, but we can study it as a mean field game. So just to recall, this is the mean field game setup we're looking at. And we're just going to look at sort of the problem that continuous normalizing flow solves, which is just minimize the KL divergence between, in this case, in this case, it's trying to learn some of flow that kind of takes your distribution pi and tries to normalize it into some sort of a normal distribution. So this discrepancy here is between rho at t and your normal distribution. And immediately you can kind of turn the mean field game's crank, right? You find the Hamiltonian. And you'll find the Hamiltonian is degenerate, right? So it's going to be 0 at 0, where p is 0, and infinity otherwise. So right away, you can say, well, if there's no Hamiltonian, or there's no well-defined Hamiltonian, then there is no optimality conditions. There's no pair of mean field games. You can't say this is a PDE. So immediately you can kind of see that these continuous normalizing flows are ill-posed as is in this form, without some sort of an additional sort of constraint involved, right? So the first thing we can do is sort of, at least in the literature, sometimes we have seen where people have said like, oh, you should make the velocity fields bounded. And so, well, let's do that. Let's see what happens. So we're going to basically say we're going to bound the set of feasible velocities. And once you add some sort of additional constraint, you'll immediately see that this mean field game provides you not only like kind of some sort of notion of well-posedness, but also the structure of what the velocity field should look like. So all we're going to do is take the same problem, just going to bound the velocity field. And if you do that, then again, turn the crank mean field games, and you're going to immediately see that the Hamiltonian is well-posed or kind of well-defined. It's c times the norm of p, and if you kind of continue with that, then it actually tells you what the optimal velocity field should look like, and it should look like basically it has a constant speed c, with the direction that is informed by u, and we know that u is going to be the solution of a Hammond-Jacobi equation. In this case, a very particular one. It happens to be a level set equation that is, and where it's coupled to the Fokker-Planck in effect. where the sort of terminal condition of your level set equation is determined by this ratio of the two of sort of approximate Gaussian to the Gaussian, and rho of the initial condition is pi here. So now, why isn't this going back to the question of why isn't this just a control problem? Is in fact a game problem? The game is because of the fact that the terminal condition on your Hammond-Jacobi equation has the solution of the Fokker-Planck. So if this were truly like a mean field, just a regular mean field control problem, the terminal condition will have nothing, like it won't really depend on the solution of the Fokker-Planck. It's because of this is, even though there's no sort of explicit interaction term, these two equations are still coupled because of this terminal condition. And this is what makes it truly fundamentally a game and not just a control problem. So you can't solve so in a control problem, you can solve the Hammond-Jacobi equation first, and then after you solve it, then plug it into the Fokker-Planck and get the sort of the evolution of the controlled Fokker-Planck. This is truly, you can't really do that. You really have to solve these simultaneously. And this sort of subtle thing makes it so that it's not just a regular control problem, but is in fact a game. And then the other question from about like, does it inform some sort of structure, even though we can't really solve this equation directly, you can already see sort of what the optimal velocity field should look like. Basically, it should just have a constant speed with the varying direction. So that already gives you some, it gives you some structure of what the optimal velocity field should look like without even doing any sort of training. So which means that if you're trying to sort of actually solve this optimization problem, you can kind of just parameterize it in a way that looks like this. And maybe that will give you something, it will maybe find the true velocity field faster in this case. Okay. The other approach is so this is also what we found is to kind of, rather than add some sort of a speed limit on your normalizing flows, this is a case where you add some sort of optimal transport cost. So in this case, Lagrangian, the running cost is 1/2 v squared. Okay. And again, you can turn the crank of mean field games and you'll see the Hamiltonian, this is a very classical problem. And in this case, the optimal velocity field will be exactly sort of a gradient field, right? It's a gradient of a scalar potential that varies with time, right? And in this case, then you'll get a Hammond-Jacobi equation that's very well studied, and the Fokker-Planck looks like, some sort of, looks like that. But the terminal condition still stays the same as the normalizing flow, okay? So again, like if you added, so at least in the so-called optimal transport normalizing flow, where they add this optimal transport cost, right away you can just say, you can parameterize your velocity field as a gradient of a scalar field, which means if you're trying to kind of learn the velocity field with like neural nets, you don't have to parameterize a neural net that outputs sort of outputs things in RD. You can just sort of parameterize the potential with a neural net and then learn the potential. And then if you want to do generative modeling, you just take the gradient of that. Of course, that's, how do you, the concept of that is a different story, but at the very least, there's a certain structure that the neural net is truly learning that you can kind of impose a priori. And hopefully that will kind of that will make things learn faster. Okay. So just to recap, so really sort of just to emphasize, there's sort of like this, there is a mathematical structure to continuous normalizing flows if you do normalizing flows in the right way, right? So in this case where it depends on, depending on how you kind of add additional constraints to your normalizing flows problem, either by bounding the set of feasible velocities or adding some sort of optimal control cost, you'll get that the velocity field will change, the optimal velocity field structure will change, and you kind of know how it should evolve. In effect, it evolves according to this Hammond-Jacobi equation. So the mean field gains basically provides sort of well-posedness and structure to normalizing flows, and maybe that might, at least in the case of the norm. Okay, so in option 1, that hasn't this hasn't been applied in practice. But in option 2, this is applied in practice, and people have found it's more stable. And with mean field games, you can kind of describe why is it more stable. Basically, it's more stable because it's well posed and it has a certain structure. Okay. All right, so that's all for me. That's all for the continuous normalizing flows. So the next one we'll do is, okay, question. Right.
Hi, sorry to ask again a question maybe. going back to the question of Romul, you don't really, I mean, at least for me, mean-free game is basically a fixed point problem. Mean-free control is finding the optimal control for the change of the distribution, but the mean-free game is more the fixed point problem. So you don't really care about the fixed point. You care about the optimizer and the feedback function, but you don't really use anywhere the fixed point, the mass equilibrium of the problem. You don't really need to.
So, I mean, this then open, depending on how you view this. So right at this moment right now, like at least in general modeling, right, they don't do that, partially because they don't know that it's actually, it has that particular structure. But if you kind of look into the work of Osher's group at UCLA, they do have methods where they're trying to solve meaningful gains based on that sort of the fixed point interpretation of things. And the idea is then, well, maybe one could sort of study these general modeling algorithms or sort of make algorithms that solve these general modeling problems based on these methods in meaningful games, right? So that is a possible future thing that people could do, right? So the idea is to, once you kind of open up sort of this connection between general models and meaningful games, you can apply other ideas from meaningful games to solve optimization problems in general modeling. But yes, in this case, we only care about the velocity fields, but it doesn't necessarily mean that we don't care about those other things in the meaningful games. It just means that maybe you could use them for future work. Yeah.
Okay, thank you very much.
Okay. All right. So the next thing we'll discuss is the we'll switch to the next one, the score-based general modeling, or some of you might know them as diffusion models in effect. And again, here it may seem very different from a meaningful game, right? Here you have two SDEs. One SDE that kind of takes your samples pi that that you like to create more of, and adds noise to it. So usually it's some sort of just like some sort of linear SDE. It adds noise until it becomes sort of just Gaussian, just pure noise in that case. And then as you sort of, and then so just remarkably that once you have this noising process, there's a corresponding denoising process, which sort of evolves your approximate, okay, in this case, because you're stopping at some finite time t, some sort of a distribution that looks approximately normal. And there's a way to sort of remove the noise so that it evolves back to your original distribution pi, at least in like the limit of infinite data. And this is how basically how score-based models work. It's, at least for images, it might be something like, oh, you have a picture of a dog, you add noise to the picture of a dog until it becomes just all noise. But as you sort of add noise to the system, you learn how to denoise it. And denoising is fundamentally based on this function here, this gradient of log eta, where eta is a distribution of the noising process. And this is what's known as the score function here. And so the idea is like, well, if you can, okay, so okay, of course, you don't know what pi is, you don't know, so therefore you don't really truly know what eta is, but if you can somehow learn not eta, but the gradient of log of eta, the score of eta, then you could create a generative model that takes samples from your normal and create more samples from pi. And the typical way of doing this is something called score matching. There are various different types of functionals, and they seem a little contrived. Basically, it just ends up being, I'm going to literally match the score. So I'm going to take some sort of a neural net S here and try to match the score gradient log eta. Of course, this is not possible to do because you don't have truly what eta is. So there are various tricks to kind of to kind of create other equivalent functionals that will kind of let you learn the score. So in this case, there's something else called the implicit score matching objective, which looks like this, equivalent to the top one, where you can learn the score without actually knowing the score, with only samples from your distribution. Okay. So this already seems very different from the regular meaningful games. First of all, there's two SDEs, not one, right? Typically in meaningful games, there's one controlled Fokker-Planck and the Hammond-Jacobi equation. So you might wonder, where's the Hammond-Jacobi equation, and why are there two SDEs where I only really need one? Okay, so if you just allow me to suspend this, if you just suspend your disbelief for a second. So this is going to be my claim. Okay, so I'm going to say we're going to claim that in fact score-based general modeling actually comes from this meaningful game here, where the terminal condition is a cross entropy. So this integral of rho with log pi. So it's actually quite, I guess, relatively simple terminal condition, since it's sort of linear in rho in some sense. And then you have a running cost, which is basically looks like an optimal transport cost, right? 1/2 v squared minus the sort of state cost. You can take f to be 0 if you just want like purely Brownian motion as your sort of kind of your sort of the drift of your controlled Fokker-Planck here. And cross entropy is well, kind of you can view it as this. If you kind of know what KL divergence is and entropy is, it's basically the sum of entropy and KL divergence. So it's almost as if so remember in normalizing flows we use KL divergence. So in some sense you can kind of view right now this cross entropy as sort of an entropy regularized version of KL divergence. So that's one way to think about it. So my claim right now is that this is the mean field game that is going to produce score-based stranded models. This backward forwards, kind of this noising denoising structure is all going to fall out from this. Okay. And so again, what we're going to do is just take this mean field game and turn the mean field game's crank and create these optimality conditions. So nothing too surprising here. There's a controlled Fokker-Planck. Because of the optimal transport cost, you know that the velocity field is the gradient of a scalar function. And then here's the Hammond-Jacobi equation. It looks sort of weird. It's fair, right? But here's a really interesting, remarkable thing is if you apply a Koh-Hop transform, so basically a logarithmic transform change of variables to the Hammond-Jacobi equation, very interestingly, if you do a little bit of algebra, and you actually find that this Hammond-Jacobi equation turns into an uncontrolled Fokker-Planck. So what was these pair of mean field game, this mean field game with a pair of equations of Fokker-Planck and Hammond-Jacobi is actually two Fokker-Plancks, one controlled and one uncontrolled. And where the uncontrolled one starts from your initial distribution, your target distribution pi in this case, right? So then if we revisit the sort of just score-based random models, right? There's a control Fokker-Planck, there's an uncontrolled Fokker-Planck, and you revisit this picture of basically there's a part where you add noise to your distribution until it becomes all noise, and there's a denoising process. You can basically view this noising process as this is a Hammond-Jacobi equation. It's just hiding in plain sight, right? So because of a very clever sort of Koh-Hop transform. And on the other hand, once the other half then becomes the control Fokker-Planck that you see before. Sorry, question?
Yeah, sorry, I have a quick question. So in the slide before, maybe, or in this one, but maybe it's clearer in the previous one. Yeah, right. So here, when you do the Koh-Hop transform, so u at time t is eta at time capital T minus t. So I see. So in the second equation, you really have, sorry, in the next set of equations, yeah, this one. So in the first line, you have gradient log eta, and this is going to be really eta at time t, right? No. Okay.
No, it'll be reverse eta at time
t, right? T, right. So my
capital.
question is, then you kind of need eta at a future time somehow, right? So eta starts at time 0, but you kind of need eta at the future time.
Right. So this is the part of the other. So in this case, so going back to the question about when are these just control problems and when are these truly games? In the case of the score-based random modeling, it's not really a game anymore. These two equations truly couple. So it is truly in this case just a kind of a mean field interpretation of a control problem. Right? Mainly because if you look at this terminal condition, this u of x is equal to minus log pi, there's no row here anymore, right? So this is no longer a game, actually a control problem. So which means that you can solve these two equations separately, where you solve the Fokker-Planck first, or this Hammond-Jacobi first, which is equivalent to running the Fokker-Planck forward, the uncontrolled Fokker-Planck forward in time first, right? And then once you get what eta is, then after you get eta, you can go back and use it in your controlled Fokker-Planck to kind of denoise the process. So yeah, so that's a very good question. I missed that. Yeah, sorry, I should have emphasized that point a bit closer. So this is no longer a game. It is a control problem. Solve these two equations separately, and this is indeed what they do in this problem, right? Solving a Hammond-Jacobi equation. Basically, this is solving a Hammond-Jacobi equation by just running a Fokker-Planck forwards, and then once you do that, you take the solution of the forward SDE and that will be the control of the denoising SDE in this case.
Okay. Okay. Thanks a lot.
Yeah. Oh, other question.
Oh, yeah. Further questions.
One more very quick question. Do you need an extra condition to account for XT or PT in like the end of the forward pass? You need to have the Gaussian. So do you put condition somewhere? At least like
Right.
in my understanding, the PT, the capital T has to be the Gaussian.
It doesn't necessarily, so because it usually runs for finite time, it's usually chosen so that eta is approximately Gaussian. It's never truly Gaussian. Of course, when you do the generation process, you could just replace eta with a normal distribution, some sort of a normal distribution that matches the moments. And then you hope that that's sort of, I mean, that's what they do in practice. They just hope that they just replace this eta with some sort of normal and then run the control Fokker-Planck and hope that's like good enough in some sense.
But just to one more, like we couldn't be able to use some form of bridge, like some form of Brownian bridge to connect to build because we need to arrive in the Gaussian, so we use some form of bridge to penalize the dynamics.
Yeah. Right. So what we found is, okay, because once you have a bridge, it's no longer really like a mean field game anymore. It really becomes like a mean field, I guess they're called mean field planning problems, I think. Mean field game planning problems. And just in practice, bridges are really hard to construct. There are certain scenarios where it becomes easier. Like if you look into like the flow matching literature recently, they have some ways of constructing bridges, but in general, bridges are really hard to kind of find in general, right? But these games are part of the reason why score-based random modeling works so well. We believe is that it's not a bridge. It's just a control. It's okay. In this case, it's really just a control problem. And the analogy you can think of is, I don't know if you recall to your early numerical analysis classes, if you just try to compare boundary value problems by shooting methods versus initial value problems, an initial value problem is much easier to solve, right? You just have to start from initial condition and you march forwards in time.
Yes.
But the boundary value problem, where you're trying to connect 2 points with like a shooting method, that's really hard. It's very unstable, right? So that's the intuition in our head, which basically like if you do like a Schrodinger bridge, for example, a Schrodinger bridge, maybe if you just extend the analogy, maybe much harder than the score-based version, because in the score-based version, it's basically like solving an initial value problem. That's very simple, or relatively simple, right? Comparatively simple, versus a Schrodinger bridge, which is like a shooting method, and that's that's going to be very finicky in the end. So even though yes, maybe a Schrodinger bridge is more precise, it's much more. It requires so much extra computational effort to kind of create, and therefore may not be worthwhile sometimes. But depends on your situation, I think.
Thank you so much.
Okay. Thanks. I think there is one more question by Romeo.
Yes, sorry, a quick clarifying question, because I got a bit lost into the reinterpretation of the Hamilton-Jacobi when you reverse the time as an uncontrolled Fokker-Planck. So just to be sure, the Hamilton-Jacobi was associated to which criterion to optimize? Something I lost on the way. So
like
you
where
had
does the Hamilton come from? So
yes.
You start from right. So L is 1/2 E squared minus the divergence of F. And you have, here's the terminal condition in effect, right? So if you take so I did skip a few steps. So the idea is just to say like, oh, here's the Hamiltonian. So here's the Lagrangian, you find the Hamiltonian, okay? And I didn't write out the steps here, but the Hamiltonian here is basically this term minus F transpose grad U plus 1/2 norm sigma squared grad U squared plus divergence of F. That this whole term here, that's the Hamiltonian.
Yeah.
Okay. And then to go from Hamiltonian Jacobi to the uncontrolled Fokker-Planck, if you just do this Kohlhoff transform with a time reversal inside of here, because the Hamilton-Jacobi is a backward equation, right? You can do some algebra. Basically, this equation up here will turn into this uncontrolled Fokker-Planck.
Okay, thanks. And then maybe it's hidden in the boundary condition somehow. No condition at time 0, right. Time peak t.
Yeah, so this boundary condition, this terminal condition here becomes an initial condition over here. This eta of y of 0 is equal to pi of y.
Thanks for clarifying.
Yeah. Okay. All right, so since we're a little short on time, let me just so I'll just kind of, okay, I won't go through the details of this, but the idea is sort of, if you're familiar with score matching, it's a question of like basically how does score matching relate to this mean field game thing. If you do some like kind of relatively technical, just relatively technical algebra in the end, there's a way to basically say there's actually like another mean field game. There's an equivalent mean field game to the score mean field game that we wrote down, we just kind of looked at. And this other mean field game is actually directly related to implicit score matching. So it sort of shows that implicit, like this score matching objective is not just something that kind of is pulled out of thin air, right? Because that's sort of how it's presented, in at least in the literature. Just like, oh, we're going to match the score. We want to find the score, so we're going to match the score. It's just kind of remarkable that the score matching objective is a mean field game, even though it looks like just like L2 minimization with the score function. There's a way to relate it to a mean field game. So in that case, so by doing score matching, you're in effect solving a mean field game. Of course, this is technically just a control problem, but somewhat an interesting sort of structure that kind of lives in here. Okay. This is just to recap. We have this, this is the mean field game, and for score-based methods, a lot of interesting sort of coincidences had to kind of line up for everything to sort of turn out correctly, right? So why is this? Why did the two equations decouple? It's fundamentally because this cross entropy term. This cross entropy term is relatively simple. It's basically like linear in row. And this is what allows it to sort of just this mean field game problem to kind of decouple into just a control problem. And this log transformation, this co-hop, is that allows us to sort of just kind of turn this Hammond-Jacobi equation into an uncontrolled Fokker-Planck. So there are a lot of things that sort of had to line up perfectly well in order for these things to work out. And just so happens that this is very useful for like general modeling in the end. So this is very particular. We thought it was very peculiar. So if you want to read more about it, it's the paper. We wrote a little small kind of look back essay in some sense. Okay. And in this case, like, okay, so just going back to the thing about like understanding general models relative to each other, then it's sort of like, normalizing flows and score-based models, they do state, kind of, if you just look at them for face value, they look very different. But then if you kind of put them inside of a mean field games context, they don't look too much different. One uses normalizing flows uses a KL. The score-based methods use some sort of a cross entropy, which is only like an entropy term away from each other. They both have basically optimal transfer cost function. One has d squared if you ignore this f here. Basically, they have the same L, and one has deterministic dynamics, one has stochastic dynamics, right? So they're not really that far away from each other once you sort of put everything inside this mean field game context, even though they seem very different on face value, like when you first see them. Okay, so the idea is then what we're sort of just in the last a little bit, we're just kind of describe like, okay, what does this give you in terms of sort of like, does this give you any practical benefit? So what does the mean field game, how can the mean field game inform how do you train your generative models in some sense? Okay, and so this is the picture you can have in mind in some sense. Like without the mean field game, what the generative model is trying to do is basically trying to say, I have a bunch of data, and there are so many models that can approximate that data. It might be like this, just think of them as they're all filled in this 3D box, and you're trying to find the best model that kind of describes your data in some sense, okay? In a way that sort of generalizes as well. But once you have this mean field game, it gives you sort of like a lower dimensional space, or kind of like another like kind of this flat, I just sort of says in this blue sheet in some sense. That sort of lives inside this space of all possible data for models. But in this case, it's like this mean field game is also informing what the model should look like. So because of this, there's structure, and then maybe you can restrict your search to a smaller space. Okay. And this is one thing that what we'll do. So this is something called a Hammond-Jacobi regularizer. So the idea is just to take the optimality conditions of the mean field game and just kind of tack it on to your training objective. So this is a typical way of training. So we'll just look at score-based random models. This is a typical way of training a score-based random model by implicit score matching. And as we just saw earlier, there's an alternative characterization, which is by this Hammond-Jacobi equation. And the idea is like, okay, well, what if you're just going to take your score matching and just tack on this regularization function, where you're just going to enforce this Hammond-Jacobi equation inside, along with the terminal condition which is over here, which is just basically, in effect, as we found, is equivalent to just score matching at the terminal condition. Okay. And the idea is not necessarily new. People have done it in the past for normalizing flows. It's just that they weren't able to do it for the terminal condition because they didn't have access to the density pi. And they found sort of kind of better, they can train their models much faster, or it has some benefit. It sort of stabilizes the training steps when you're trying to find a generative model. Okay. And for us, at least we did some preliminary experiments, and we kind of saw, like, we're just trying to explore around what this sort of does. So here's a case of a checkerboard distribution up in the top left. It's sort of discontinuous, right, at these boundaries. So it's relatively somewhat difficult to do with score-based models. So if you decide just to do a score-based generative model directly, you'll get this one on the top middle here, where you see, like, okay, it captures the shapes pretty well, but it's a little diffused, right? Because fundamentally there's a diffusion equation inside of there, right? But what we found is that, okay, once you impose these terminal conditions, you actually find that it can actually inform the edges a little bit better. And depending on how you turn on and off these different sort of terms in your regularizer, you'll get different quality generative models, right? So most of which are better, or some of which are better than just doing it without any sort of regularization. So then this becomes like a way of sort of experimenting with different parameters, or like by adding different constraints into the optimization, right? So once you have this, there's sort of a new or whole new world of trying to kind of, you can tune your generative models in a way, in a better way, because this is sort of like what score-based generative models is fundamentally doing is solving this Hammond-Jacobi equation. So why not just tell it that information as it's training? Okay. You can also just say, let's just throw out score matching altogether and just solve the PDE by just matching. So this is, I guess, if you're familiar with PINs, physics-informed neural networks, it's somewhat similar to that in this case, where we're just going to say, we're not even going to do the score matching objective. We're going to solve the Hammond-Jacobi equation and just see what it produces. It already produces something. Okay, it's not as good as, like, just, if you have the score matching objective, but it already produces something pretty good, interesting. So maybe someone could just take this and make a generative model out of it by some extra tuning. Okay. So, and then we have some like forthcoming work basically where you try to hard code a model that solves the Hammond-Jacobi equation a priori. So basically something that's create a neural net. It can create some sort of a model, it's maybe a neural net that solves the Hammond-Jacobi part of the equation exactly, and then do score matching with that model. And in that case, then, because you've informed the model with like so much of what it should look like, it can find the truth really quickly. So this is a case where, okay, so here's some preliminary results where we took some, here's sort of like two spirals in effect. If you did regular score matching, you're just going to get a lot of, with a neural network, you're just going to get a bunch of junk. But then because you kind of told the model what it should look like a priori, it can find a good general model really quickly, in effect. So the whole idea here is basically by sort of restricting, by kind of using the mean field games to kind of inform what the model should look like, you can sort of restrict the space of models that you should look at. Okay. So since I don't have much time, this is just, I'll just leave it. I'll just say something real quick about this. We also kind of found like a version of something called there's something called a Waschstein gradient flow, and we found sort of a mean field games formulation for the gradient flow. It looks like this. It's not, I mean, for face value, it's not super interesting unless you're really interested sort of, if you're interested in solving this mean field game, we'd be very interested in hearing what your thoughts are. We just sort of wrote it down, and we just know that, like, oh, here's the Waschstein gradient flow. It's also used in general models, and just so happens to have some sort of connection to mean field games. Maybe somebody could do something with this later on. Okay. One interesting connection is this gradient flow formulation that we have. Depending on what limits you take, you kind of reproduce interesting things. So in one limit, you sort of get just the regular Waschstein gradient flow. But in the other sense, you can also get sort of this optimal transport normalizing flow that we talked about in the beginning. So this is actually some sort of an interesting way to sort of interpolate between two curves, or not really interpolate. It's like in some sense, interpolating between two types of flows, a Waschstein gradient flow and an optimal transport normalizing flow. So it's kind of like it's sort of like interpolating between straight lines and just gradients flows in some sense in the space of probability distributions. I mean, we don't know what to do with this at this point. We just kind of wrote it down. We're just like, oh, this is kind of interesting and neat. But if somebody has some ideas, we'll be very open to hearing about it. Okay. So I'll just leave you with this. So the idea is like, okay, once we have all this, we have this sort of this formulation with mean field games. You can place into context a lot of different types of mean field games in the general models as mean field games. So basically, depending on how you choose your terminal costs, interaction costs, and running costs and dynamics, you get all these different types of sort of well-established generative models. So this is all stuff that's like sort of well-known, that's known in the literature, and we can't put them inside this interesting playground. And then we said like, okay, once you do that, you can also start creating sort of inventing new ones. So down here, we have sort of like, oh, here are some possible new ideas that people could do based on our sort of playground that we this laboratory that we kind of set up. So we present this as, the laboratory because of this chart in effect. So you can sort of experiment with your own algorithm here and by just choosing different types of cost functions. We're not saying that every formulation will lead to a good general model. This is simply sort of like a kind of a nice little sort of laboratory for you to experiment. Some may be good, some may be bad, but it requires experimentation within this laboratory. Okay, so I'll just leave you with this. So the idea is successful generative flows and diffusions are mean field games. By putting in terms of mean field games, just sort of a common backward-forward mathematical structure. Backward equation determines the optimal velocity field with the Hammond-Jacobi equation. A forward equation, which is a control Fokker Planck, determines generation, and just so happens to apply to basically almost all, at least as far as we know, all flow and diffusion-based models. So some other things that it's in the paper that we didn't really talk about, you may know about the score probability flow. It's also a mean field game. In this case, there is an interaction term. You can actually have an efficient information as an interaction, and it produces something called the score probability flow, like a deterministic version of a diffusion model in effect. We do talk about the Schrodinger bridge, although it is a little different from, it's not exactly a game. It's really sort of a planning problem, I guess. And some sort of other interpretations of optimal transport, cross-entropy regularized optimal transport, because once you kind of view score as a mean field game, there's also another interpretation as like some sort of cross-entropy regularized optimal transport. And if you know about Boltzmann generators, we kind of, I don't know, suggested a fix for them in some sense. They're not very well posed. So I'll just leave it there, but yeah, so thanks again for your attention. Yeah.
Thank you very much, Benjamin. It was a very nice talk. I think very clear, and it connects many things. I don't know if there are some questions. I have one quick question, maybe, unless there are other questions from the audience. So I'm wondering if, so here this is really for models that are based on diffusions, or at least, I guess you could even like kill the diffusion, but at least some dynamics is involved between time 0, time t. And with Singo, who is in the audience, I guess we looked at some connections between mean field games and GANs, which are also used for generative models. And so I'm wondering if you have also looked at connections between GANs and mean field games in the framework you are using here, or if for you it's really a different paradigm, the GANs and the diffusion-based models.
Yeah. Actually, so one thing, yeah. So it's a very good question. So we do have an ongoing project with GANs and sort of a GANs version of and how it relates of a general model and how it relates to the mean field game. And then really sort of this mean field game interpretation really sort of also helped us sort of crystallize that GANs is a little different from like these flow and diffusion models. So it's a very different animal, just in the sense of like, here, let me go back. So, okay, unfortunately I don't have a slide on GANs, but let's just take this problem. Take this, this problem, right? So GANs typically, it still might look like this, infimum of KL divergence. And if you're familiar with GANs, the idea of a GANs is basically you take it's sort of a minimax problem, right? And where the minimax sort of comes from, so the min comes from this inf, but this max comes from sort of a variational interpretation of the KL divergence. So you can take the KL and write it into a soup over functions phi, right? And then the functions phi then becomes sort of the discriminator inside of a generative adversarial network. So the adversarial comes from the minimax, generative comes from the flow in this case, right? So GANs is really just a way of sort of dealing with this divergence in some sense. So it's not really like a choice. You can either use a flow or you have to use a GANs. You can do both by basically saying, oh, my generative model will be a flow, but I'm going to train it with KL divergence, but train it in an adversarial way. We're just going to say we're just going to take the variational formulation of KL and then train the flow that way. So there are people who have done that. So if there's this paper by Irman's group, it's called the flow GAN, where they basically take the generative model as a flow, but they train it in a GANs way.
I see.
So in that sense, yeah. So there's a lot of interesting things there. So so they don't do it in a way where they keep the mean field game in mind. So they're just still solving this problem directly. And as we've kind of went through, it's not well posed, right? This is the Hamiltonian general. If you do it like this on its own, you might get multiple solutions depending on how you parameterize the problem. So one kind of ongoing thing we were thinking about was like, okay, what if you just sort of take the OT flow, or not, like either this one or like this one, for example, and just do KL in the GANs way and see how well that works. So that's sort of one thing that we kind of thought about. And yeah, so that's so it's not an either or thing. You can do GANs and simultaneously.
I see. Yeah, very clear. Yeah. Thanks a lot. I think it's very helpful. Thanos, I think you have another question, maybe.
Yes, I have a question, but also a comment for you. This article is about generative with diffusion models combining with GANs. Maybe I can send you later the article, but there is already people doing some stuff. Yeah. My question is, diffusion models, at least like the plain diffusion models, they are known to be slow. Among all the models, they are known to be slow. Do you know, or like the mean field interpretation you think that could give insights to speed them up? Or would you comment on consistency models if you have seen them around, like they popped up recently?
Like speeding up in the sense of how do you choose like an F to speed them up in some way or something else?
But basically, the problem of like being slow is because you need the end point to be Gaussian, the R capital T. You take like many steps because the central limit theorem says that in the infinite time you will arrive at the Gaussian. So you need many times. So this makes it slow. You need to iterate many times to arrive. So this is what I mean slow. And do you think that the mean field interpretation could give some insight how to speed them up?
Not so we have some stuff that kind of depends on how you or how to say this with this mean field sort of interpretation of things. You can kind of take it in different directions. So like one thing we were thinking about, like like Osher's group thinks about these kind of new methods for numerically solving mean field game problems. So one thing, as we were talking to them, we were hoping that maybe they have some sort of way of discretizing the problem so that you don't have to take as many steps, for example. But along the way, we kind of found that maybe potentially, I mean, at least if you just take this for face value, like this mean field game problem for face value, in some sense, what is the benefit of learning the score, right? It doesn't really, because in some sense we kind of know what eta is. Because you're adding a lot of noise to it, right? So if you think about this case where if you just have samples from pi and you're trying to find how pi evolves over time with added noise, pi will go to a Gaussian, relatively speaking, still quickly, right? Of course, maybe if you want to kind of study the score, it will take, if you want to find a score function, it'll take, you'll have to simulate for a long time. But you can write down sort of like an approximation to the score relatively easily by just using some sort of a kernel formula, in effect. So part of the thing we were kind of looking at is well, we know if you know, so okay, so going back to kind of like, well, how do you know, how do you accelerate this a bit faster? So I don't know if there's a way to make this, if this can inform how do you make your distribution become Gaussian faster. But what this can do potentially is to describe some sort of a model, like some sort of a model for the score, so you don't have to train for as long because you know what the score should look like, right? Based on sort of like how it solves the mean field game. So you can create some sort of a model that will train faster. So you still have to simulate for just as long, but it will train faster because you know what the score should kind of look like. That's partially how we created these images here. Here, let me try to zoom through the images. Here, right, where we kind of created a model for the score that's informed by the Helmholtz-Jacobi equation. And because we know, it's sort of like, if you're trying to learn a periodic function, but you only have exponentials as your basis, it's going to be really hard, right? The analogy would be, we know that the function is sort of periodic, so we should fill the basis with sines and cosines. And once you do that, it becomes much easier to learn. This is sort of like what we're doing here, which is sort of saying like, oh, like based on the information on the mean field game, maybe you can construct a model that expresses the score in a better way. So in that sense, we're not really cutting down on like the simulation time, but at the very least, it will be easier to train because we know what the model should look like. Sorry, roundabout way of answering your question.
Yeah.
No,
thank you very much.
Yeah.
Okay, thanks a lot. So I don't see any further questions. So yeah, thank you again very much for the very nice talk.